Just look at this. Movement, right? It's literally everywhere, all the time. But here's a question for you. How would you describe that motion? Not with words, but with math. How do you actually capture both the speed and the direction of something in one single clean idea? Well, it turns out there's this kind of secret language for that. It's what physicists, game developers, and programmers all use to build and describe their worlds. And today, we're going to learn how to speak it. We're talking about vectors. All right, so before we can get anything moving, we've got to know where things are in the first place. Think of it like you're loading up a video game. The very first rule is just knowing where stuff is on the map. So what even is a vector? Let's forget all the arrows and physics stuff for just a second. At its absolute core, it's just a list of numbers, and that's it. For a flat 2D world, it's a list with 2 numbers. For a 3D world, a list of 3. The only catch? The order is absolutely crucial. You know, you might think a point and a vector are the same thing, but there's a really cool difference. See, a point, written with parentheses, is just an address. It's like dropping a pin on a map. But a vector, with these angle brackets, is more like an instruction. It's a set of directions. From the very center of your world, go 3 steps over and then 4 steps up. It has this idea of travel baked right into it. And that's exactly what we call a position vector. It's an arrow that points from the center of our map, what we call the origin, to a specific spot. It's the perfect way to give an address because it doesn't just tell you where you're going, it tells you the exact path and distance to get there from the start. Okay, so we've placed our character on the map. Cool, but they're just standing there. So how do we make them move? How does our character actually get from point A to point B? Believe it or not, the answer is super simple. We just add the movements together. This is called vector addition. Basically, if you make one move and then you make a second move, vector addition tells you the single, direct move you could have made to end up in the same spot. And here's how you can picture it. It's called the head-to-tail rule. Let's say vector U is your first move. Then, right where that move ends, at its head, you start your second move, vector V. The final result, this new vector, is the shortcut. It's the straight line from where you originally started to where you finally ended up. And the math for this? Oh, it's even easier. You don't need to draw anything. You just line up your 2 lists of numbers, you add the X numbers together, you add the Y numbers together, and boom, that's your new vector. It's really that simple. So if adding is for combining moves, what's subtraction for? Well, it's for finding the path between 2 things. This is how a video game enemy knows the exact vector to get to you. It's answering the question, what move do I have to make to get from where I am to where you are? Okay, so we can set a location, we can combine moves, but what if we want to change the power of a move? You know, how do we make our character suddenly run twice as fast or jump half as high? Well, that brings us to something we all get from video games, the power-up. We need a mathematical way to power up our vectors. In math, this power-up is called scalar multiplication. Now, scalar sounds fancy, but it's just a plain old number, not a vector, just a number. And when you multiply a vector by a scalar, you're either stretching it or shrinking it. You're changing its length, its magnitude, without changing the direction it's pointing. Think of it exactly like a speed boost. If your vector represents 1 step forward, multiplying that vector by 2 gives you a new vector for moving twice as far in that same direction. Multiplied by 0.5, now you're in slow motion. You're just scaling the original move up or down. Now, here's a neat trick. If you take any vector and scale it down so its length is exactly 1, you get something special called a unit vector. You can think of it as the pure essential direction of that vector. It has no power on its own, it's just that way. It's like a single tap on a joystick, which we can then power up using scalar multiplication to control how fast we go. So, let's take a step back. We have our building blocks now. We can define a place, we can combine moves, and we can power them up or down. What happens when we put this all together? Because this is where it gets really mind-blowing. It turns out that those 2 incredibly simple rules, just adding vectors and multiplying them by numbers, that's it. That's all you need. That's the fundamental alphabet you can use to write the instruction manual for an entire universe. This idea is called a span. And what it means is if you just take 2 basic vectors pointing in different directions, let's say a move right vector and a move up vector, you can reach any possible point on a flat 2D surface just by scaling and adding them.
A little bit of the up vector, a lot of the right vector, and you can go literally anywhere.
Now get this, take that idea and just add one more basic vector, a third direction, like move forward, something that pops out of the screen. With just those 3 simple vectors, you can combine them to pinpoint any location in the 3-dimensional world we live in. So, what's the big takeaway from all this? It's that the entire complex reality of space and movement, everything from a video game character to a planet flying through the cosmos, can be built from just a few simple, scalable directions. And that kind of makes you wonder, if our own reality can be described with such a simple alphabet, what other parts of the universe are just waiting for us to learn how to